So we're going to look at chapter 16, solubility and complex ions, and we're going to use version 2 of the review document. And I've got all right. So here's, let's see, this is, you put version 2 at the top, it must be at the bottom here. Yeah, this is version 2. We're going to start with number 5. Start simple and work our way up. Okay, so we've got barium carbonate. Most of the carbonates are insoluble by CHEM101 standards. It's really slightly soluble. So what barium carbonate is supposed to do is, and you have to write it correctly, right? If you can't write that correctly, then you're dead in the water. Barium is an alkaline earth. It's 2+ charge. Carbonate is a polyatomic ion with a 2- charge. So you just need one of each, and that's a solvent. And then it's going to be set up in equilibrium with just this and this. Go. So that's the controlling reaction, that reaction of interest. We also know that the solubility is given as 4.03 times 10⁻⁵, and that's in molarity. Whenever we say solubility, in this context, we mean molarity. That many moles per liter of this goes into solution. So that means for every one of these, one of those, and for one of those, one of these. So all we need is to set up our unknown so it's equal to one of these, because this one doesn't enter into the expression. We're looking for the KSP. So the KSP is going to be written, obviously, to the first power and carbonate to the first power. That's it. So we looked at, I'm going to drag this out for the first one, just to do it step by step, and then we'll abbreviate later on as time gets short. So initially, what do you have? Right? Nothing. Right? Nothing's there. So what's the change? Well, the change is you're going to have an addition of one of those. And we're told that the solubility is 4.03 times 10⁻⁵. So 4.03 times 10⁻⁵. Moles of this per liter go into solution. So that means since this is 1:1, it's exactly the same number here. And this would be, okay, and this is molarity. So at equilibrium, obviously you're going to have this one and this one. Okay, so if we plug those numbers in here, we can find out what the KSP is. And that's going to be this one times this one's the same. So all we have to do is, for brevity's sake, just square it, correct? And squaring it should give us 1.62 times 10⁻⁹. And we don't put units. Okay. That one's fairly straightforward. We'll do the easy ones first. And number 6. Go. So the correct mathematical expression for finding the molar solubility of 10,2-hydroxide. We'll do this. We'll stretch this one out a little bit so that we can learn how to use the shortcut. This is going to give us 1 10 ion and 2 hydroxide ions. Okay. So if we did our ice table, we know that to find the solubility of this, 1 mole of that goes into solution. One of these, 1 molar here, 1 molar here, but twice as much here. So if we start off with 0 there, and we're going to have the same number, the same molarity here in solution as here, because these are 1 to 1. Okay, so we choose our unknown correctly, then we can solve for that. We know that that's the answer. We don't have to do any post calculations. But for every one of these, 2 of these goes into solution. Right? So that means we have S and 2S. And if we're solving for KSP, it just wants the formula. The KSP would then be that one and this one squared. So that means this value would be S and this value would be 2S squared. So that would be 4S squared times S would be 4S cubed, correct? And that would be D. Okay. All right, 611. Which of the following compounds has the lowest solubility in moles per liter in water? Molarity. Okay, one thing you'll notice from these is that you don't have the same number of cations and anions going into solution for each one. So we cannot do a direct comparison of the KSPs. Or I think I mentioned that during the lecture. If each one of the compounds that you're comparing has the same number of cations and anions of each one going into solution, you can compare directly the KSPs. But in this case, you can't. We have to calculate the solubility for each one and compare the ultimate values. So what we need here is Henry Ford. Set up an assembly line. All right, so we got silver, phosphate, we got hydroxide, we got cadmium sulfide, calcium sulfate, and aluminum hydroxide. All right, we're going to compare the solubilities. We want that S value. Right? So if we follow, I should do each one of them for this type of problem. So let's just do that. If we do the assembly line, then it shouldn't be too much trouble because we're going to do them the same way each time. Okay, we've got 3 silvers and 1 phosphate. And I'm leaving out the aqueous because we know they're in solution. This one is going to be like we had it before, and 2 hydroxyls. 2. Okay, so far so good. Cadmium is a 2+. Sulfur is a 2-. Calcium is 2+. Sulfate is 2-. And then aluminum is a 3+. And then 3 hydroxyls. Okay. So if we use the S as the solubility, then the KSP for each one, we might as well write those up here now. The KSP for this one is 1.8 times 10 to the minus 18. And, oops, 3 times 10 to the minus 27. So the temptation here is to say, all right, the smallest KSP is for this one. So we're thinking, you know, it should be the least soluble. 1 times 10 to the minus 28. And 6.1 times 10 to the minus 5. And 2 times 10 to the minus 33. So each one of these is equal, if we assign S, the solubility for each one of these S, then for every one of these that goes into solution, one of these forms over here. But 3 of them form here, right? Circular hidden knots, right? Okay, so every one of these, this is like this, we did this before. That was 2S. This one is S and that one's S. That's 1 to 1, 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 3. Yes, for every one of these, you get 3 of those. Okay, so now you can look at the coefficients and you know what power. So this is 3S to the 3rd power times S. And this one is S times 2S to the 2nd power. You do this. There you go. Because of the coefficient. This is just S times S. This one is S times S. This one is S times 3S to the 3rd power. Okay. So now we just need to solve for S for each one. All right, this is going to be 3 times 3 times 3 is 27. Equals 27S to the 4th power, correct? 7 S cubed times S, yeah. This one is 4S cubed. This is S squared, and this one is same as that one. Okay, so let's see what's S equal to for each one of these. Now for this one, we take that value and divide it by 27, and then take the 4th root. Okay. Some of your calculators have a root. They have squares and square roots. They have powers, and then roots, multiple roots. Mine doesn't do that. I have to use a trick. But if we take 1.8 exponent 18 divided by 27, then I need to take the 4th root of 6.67 times 10 to the minus 20. So for me, the 4th root is the number to the 1/4 power. Remember that from math? The inverse of the root number as a power is the same as the root number of that. So I just need to punch this in and say 0.25 is 1/4 and go to my power key. And that's 1.2 significant figures, 1.6 times 10 to the minus 5 molar. Okay. So now I just go to the next one, exponent 7, divide by 4, and take the 3rd root. So that'd be 0.3333. Would be 9. And that's only one significant figure. 9 times 10 to the minus 10 molar. And so we got this one, got that one. Okay, this is just the square root. 1 exponent 28, change the sign, do the square root. That's the 1.0 times 10 to the minus 14. I should have been able to do that one in my head. Right, just half of that value. And the square root of this one. Well, can't do this one in my head because it's got the coefficient here. 6.1. Exponent minus 5. And then take the square root of it. Is 7.8 times 10 to the minus 3. There we go. And the last one. 2 exponent 33 minus there. And take 27, divide it into it. And take the fourth root, 0.25 for me. And so this is one significant figure. So I got to say 3 times 10 to the minus 9. Lord. Okay. So, and been at it so long, I forget the question. Lowest solubility. So we need the smallest number. Minus 5, minus 10, minus 14, minus 3, minus 9. This one right here. This one has the lowest molar solubility. Okay. I know that's a lot of work. But we do what we have to. We keep the prize in our minds. What's at the end? The answer's at the end. Whatever it takes to get there. Oh, any questions? No, we just do assembly line. All right. It's 11. 13. So we're looking for molar solubility of barium carbonate in 0.1 molar barium chloride solution. All right. So we're looking for the solubility of barium carbonate. We did something like this earlier, except we were looking at pure water. Now what do we have to deal with? There's two words. Common ion. All right, so if we set up our ice table, initially, we have molar solubility in barium carbonate in 0.1 molar barium chloride. Okay. All chlorides are soluble, so we're not interested in almost all chlorides are soluble. Barium chloride is soluble. We know that because we're given 0.1 molar. So what's the common ion here? Common ion is barium. Right? Barium is already 0.1 molar concentration. Okay. So what's that going to do to the solubility from what's it, number 5? It's going to decrease it, right? Because we've already got some of this, which if we try to add more over here, this tends to push the reaction back that way. Okay, so molar solubility. All right, so this is 0. So we are going to get some of it, 1 to 1. So we are going to get some of this, and we are going to get some of that. Same amount. Like for every one of these, you get one of those and one of those. But the equilibrium expression is 0.1 plus S and S. So now if we know the KSP is 1.6 times 10 to the minus 9, And that's equal to this expression. Then we plug in our values here. So we have 0.1 plus S times S. Okay, that's going to give us a quadratic equation, right? So the question is, are we justified in saying S is so small it doesn't matter? Well, we know that let's see, what was the solubility for, measured? No, we did the KSP. Solubility was 10 to the minus 5. The solubility is going to be less than 10 to the minus 5. Because that first problem we did, number 5, was in water. And the solubility was given to us as 10 to the minus 5. So it's going to be a lot less than 10 to the minus 5. I think we can safely ignore that S. 0.1 S then is equal to that value. So we just need to divide this one by 0.1, which is the same thing as multiplying it by 10, correct? So S would be 1.6 times 10 to the minus 8. Well, none of these. Right? If we went the wrong direction, 1.6 times 10 to the minus 10, you might say A. But this should be 1.6 times 10 to the minus 9 divided by 0.1, right? Divided by 0.1, or 10 to the minus 1, is the same as multiplying this one times 10 to the first power, which is why I went from 10 to the minus 9 to 10 to the minus 8. Okay? All right. Right, so the answer is not up there. None of these. All right, 13 is next. 17. Which of the following solid salts is more soluble in 1 molar hydrogen ions than in pure water? All right, if we've got 1.0 molar there, we've got each one of these Ne. Okay, so sodium chloride, calcium carbonate, calcium chloride, silver chloride, and calcium nitrate. Okay, what effect does acidity have on any of these? Remember the two ways that we get slightly soluble compounds into solution? There are two ways to do it. One is you introduce hydrogen ions, make it acidic. What's the other way? The other way is what we're doing today. You make a complex ion. So under what circumstances does each one work? When does this make the compound more soluble? When the anion is the conjugate base of a weak acid. So if it's a weak acid and it dissociates into that and that, if this is a weak acid, what's this? That's a strong base. So if you put hydrogen ions in there, this is going to grab it. Right? So what we're looking for here is the anion. We want to see if the anion is a strong base. So you look at what was its source. What acid could it have come from? Right? This would have come from nitric acid. Right? Strong acid, weak base. Hydrochloric acid, strong acid, weak base. Same thing here. How about this one? H2CO3, weak acid, strong base. And the same up here. This is the only one for which the hydrogen ions will drive this reaction to the right. Right? Minus. So if we add hydrogen ions here, right, what's it going to make? Well, it'll make this one first, of course. And then it'll probably pick up another one and make this one. Right, so we're extracting carbonate from this side and driving that one to the right. Makes it more soluble. This only works if the anion is a strong base, a strong conjugate base. Okay. If it's not, then we have to go to the other option. You attack the cation instead of the anion. And if you attack the cation, you've got to make a complex ion out of it somehow. Okay, so the answer to this one should be B, calcium carbonate. That becomes more soluble in acidic solution. All right. Who's next? 19. Let's see, I can see that one. All right, you have a solution consisting of 0.1 molar chloride and 0.1 molar chromate. You add 0.1 molar silver nitrate dropwise to this solution. Given that the KSP for silver chromate is 9 times 10 to the minus 12, and that for silver chloride is 10 to the minus 10, which of the following will precipitate first? All right, so let's extract information from that one. We're looking at two possible solubilities, silver chromate and silver chloride. Chromate. Yep. Wait, this should be two. Yep. All right. Here's the problem. Remember how it was said polyprotic acids go one proton at a time? This one should go one silver at a time. I have to assume that that value, 9 times 10 to the minus 12, is for both silvers. I have to assume that, or otherwise I'm stuck. And then we have silver chloride, which makes this one, let's say aqueous, and chloride. And the KSP for this one, 1.6, is it? Yeah, 1.6 times 10 to the minus 10. Okay. Which of the following will precipitate first? Right. If this one is okay, 0.1 molar chloride and 0.1 molar chromate in solution. Okay. The solution is composed of this chromate and this chloride in solution. So how do we get them in there? We have to use some soluble form, like sodium chromate or sodium chloride or potassium chloride would work here. But you have to get these in solution. So these are in solution, and there's no silver. We're going to titrate with silver. Okay, 0.1 molar silver nitrate dropwise. Okay, so we're going to add 0.1 molar, just say silver ions. Okay, so we're going to add this and this. Which one precipitates first? The one that precipitates first is the one that has the smallest solubility product. Excuse me. We have to compare. This compares the solubility product. We need to compare the solubilities. So what's the solubility of? Well, the solubility here would be, right, if this is S, this would be 2S squared. And this would be just S times S. So we take the square root of KSP, we find out the solubility of silver chloride. Square root of that is 1.S equals 1.3 times 10 to the minus 5 molar. And this one would be 4S cubed. So say 9 exponent there, and divide by 4. And then take the cube root, the cube root of 0.333. There, so I get S equals 1.3 times 10 to the minus 4. Okay. So the one that's the least soluble is silver chloride. It's the one that's going to precipitate first. The reason for that is as we add silver to this one, which one, the Q value, before any reaction occurs, the Q is going to steadily increase because we're increasing this value right here. So which one will the Q exceed the solubility? It's this one first. 10 to the minus 5 versus 10 to the minus 4. So silver chloride is going to precipitate first. And we can actually use that, right? We can precipitate out silver chloride first, and when it's all gone, actually there is some overlap, but you can get most of this out. The chloride, you can get the chloride out before you get to the chromate. Right? You can do it stepwise. Hope that makes sense. That was 19. Let's see, 21. How many moles of calcium nitrate must be added to 1 liter of 0.182 molar potassium fluoride solution to begin precipitation of calcium fluoride? Calcium fluoride KSP equals 4 times 10 minus 11. Okay, so we've got a titration problem going on here. The reaction that we're interested in is the precipitation of calcium fluoride. So we've got a calcium and 2 fluorides. All right. We have 1 liter of 0.182 molar potassium fluoride solution that is going to be we're starting off with 0.182 molar potassium fluoride. So this concentration initially is 0.182 molar, right? In order to perform an equilibrium calculation, ultimately you have to go to concentrations. Sometimes we can simplify things by doing absolute numbers of moles. That's part of what we'll do today. But ultimately, the equilibrium is established by concentration. So we got 0.182 molar. There's 1 liter of this. And then how many moles of calcium nitrate must be added to begin precipitation? So when does precipitation begin? Precipitation begins when the Q exceeds the KSP. Right? So the KSP would be written as calcium and fluoride squared. And the Q, we just have brackets, parentheses instead of square brackets. Right, so what concentration of calcium do we need at equilibrium? So what we're looking at here is what concentration here do we need in order to give us a Q that exceeds this value. And let's see, that value was 4 times 10 to the minus 11. Okay. So we want, let's see. We're going to add so much here. And that means that we're not going to add anything here because we're adding in this calcium nitrate. So actually we've got an X here and we've got 0.182 here. Correct so far? Okay. So if we plug those values in, X for this one and 0.182 squared for that one. And that's if that's equal to this one. We just need to find out X is the breaking line. If we exceed X by any amount, then we're going to create a Q value that's larger than the KSP. Right? Okay, so let's solve for X. Let's see. 0.182 squared. Squared. So this one is 3.31 times 10 to the minus 2. So if you take this one and divide it into that one, then we get X equal to 1.2 times 10 to the minus 9 molar. That's our breaking line. 1.2 times 10 to the minus 9 molar would be here. That would give us Q equal to K. Right? So if this is the molarity, it's asking us how many moles. Right? How many moles? Well, there's one of 1 liter. We have to assume that when we add, we're not changing the total volume much. Right? When we add calcium as calcium nitrate, in fact, we are. Right? So we would definitely have to exceed this amount, and the moles is equal to molarity times volume. Remember that one? So this one times volume, 1 liter, is equal to 1.2 times 10 to the minus 9 moles. So that's how many moles of calcium nitrate, because calcium nitrate gives us this, for every one of these, there's one of those. So if we say, we know that this is so many moles of that, it's the same for this, right? 1 to 1. So 1.2 times 10 to the minus 9 moles is the minimum amount of calcium that has to be added. Did I lose anybody? Are you still bleary-eyed from holidays? Okay, so the answer is D. We have to kind of think of that one in reverse, because rather than working this way down, we're working from this way up. Because we're adding this one and it's going up here and driving it that way. So that's where we have to think in terms of Q versus KSP in order to determine the end point or the equivalence point for this titration. Let's see, I can get those on there. 23. We're doing on time. I might have to come back after lab. A solution is 0.01 molar in each. Lead 2 nitrate, manganese 2 nitrate, zinc 2 nitrate. Solid sodium hydroxide is added until the pH of the solution is 8.5. Which of the following statements is true? No precipitate will form, only lead hydroxide, only manganese, only zinc and lead will precipitate, or all 3 hydroxides will precipitate. Okay. So the reactions we're interested in are the hydroxides becoming soluble. And the KSP, this one is 1.4 times 10 to the minus 20. So let's see, we'll move down to this one. The nice thing about this calculation is that they all form the same number of moles. Right? You got one of these, one of these, one of these, one of these, and the same thing for zinc also. Solid. Okay, and this one is 2 times 10 to the minus 13, and this one is 2.1 times 10 to the minus 16. Okay. So in order to determine which one precipitates at 0.1 molar for each one of these. Yeah. 0.01 molar. There we go. What else do we know? We know the hydroxide concentration. We haven't calculated it yet, but we can because the pH is given as 8.5. If we increase the pH to 8.5, what's the pOH? 14 minus 8.5. Right? In order to find out which one of these Q's exceed the K's, we need to know the hydroxide concentration. So that would be 14 minus 8.5 is 5.5. Okay, what's the hydroxide concentration? Well, it's 10 to the minus 5.5, right? Okay, Change that sign and go to 10x. So this is equal to 3.16. That's 10 to the minus 6. So we know this one is 3.16 times 10 to the minus 6. These are molars. Okay. So what's the Q calculation going to look like? Q for this one? Well, it'd be this value, right? Oops. Be consistent here. 0.010. And then this one is 3.16 times 10 to the minus 6 squared. Actually, that calculation is going to be the same for each one of them. So let's see. I already got this one in, so let me square it here and multiply it times 0.01. So that's 1 times 10 to the minus 13. 1 times 10 to the minus 13 will be the Q for each one of these reactions. Now, which ones will be Q will exceed the K, right? 10 to the minus 13 is bigger than 10 to the minus 20, right? So this one is Q exceeds KSP. How about this one? Right, that's smaller than this one, right? Same powers, but this one is less than 2. So this one, the Q is less than KSP. And this one, minus 13 is bigger than minus 16. This one is Q greater than KSP. So at that pH, only the lead and the zinc will precipitate. So that's why the answer is D. Okay. All right. Three. 24. Okay. In a qualitative analysis scheme of metal ions, our analytical group 2 cations separated from analytical group 3 through 4. 2 separated from 3 through 5, excuse me, 5. Right, so we need to look at the scheme. Right, you go back. Let's go down to the bottom. Let's see, can I get there here? Yeah. Go down to the bottom. You'll have this one available. Just look at this one. Okay. So how did we separate group 2 from 3 and 4? Right. There's group 2, and we add hydrogen sulfide in acidic solution. Right. We've got 2 through 5 group here. If we add hydrogen sulfide, and it's already acidified under this schematic, so if it's acidic and we add hydrogen sulfide, then we'll get group 2 separated out, this one, from 3 through 5. So we need to add hydrogen sulfide under acidic conditions. All right, so let's go back up. See if I can do this. Number 24. There we go. So by adding hydrogen sulfide, these two maybe under acidic conditions forming insoluble metal sulfides. So C is the answer. And all you have to do is just look at the chart. $25. Okay. Which of the following solid salts should be more soluble in 1 molar ammonia than in water. Okay, this is our second way of putting slightly soluble compounds into solution. Right. Sodium carbonate, potassium chloride, silver bromide, potassium nitrate, and none. Okay, and we're going to add 1 molar ammonia. So which one's going to be more soluble? Well, we have to look at the cations. Which one forms a, if we're going to put them in solution, oops, need that one. Actually, that's kind of dumb. This is completely soluble to begin with. This one's completely soluble, right? This one is only sodium carbonate. Yeah, that one's soluble, right? All alkaline metals are soluble, right? So by process of elimination, it's either E or C, right? We know that the halogens of silver are only very slightly soluble. And we can't attack this one. We're not attacking it with acid, we're attacking it with base. So will this silver form a complex ion with ammonia? And the answer is yes. Right? It does the same thing that we're going to do today. Right? So that was kind of a no-brainer, really. But in the heat of an exam, you know, it can get confusing if you don't stop and think about it. Let's see, 27. All right, this looks like we're going backwards. The correct mathematical expression for the molar solubility of lead-2 chloride. Lead-2 chloride gives us 1 lead. Oops, that's blading. Lead. And 2 chlorides. Right? So if we want solubility of this, 1, 1, make that one S. That means we get 2 of these. So the KSP is going to be S, 2S squared. And so we have 4S cubed, right? We did one of these before. Kind of a duplicate. 27. All right, which of the following leads to the formation of precipitate? This is kind of going backwards. We know a precipitate will form if the Q is greater than the KSP. Right, so C has to be the answer. That's just definition. Let's see here. What's the solubility of silver chromate in 0.049 silver nitrate? 34. So we're looking for the solubility of this compound. So it makes 2 silvers and 1 chromate. And the KSP should be given as 9 times 10 minus 12. There we go. Okay, so initially, in this case, we do have some silver already there. There is a common ion, 0.049 molar. Right? And we have no chromate. So we know it's going that way. And we're going to have, for each one of these, we have 2 of these. So at equilibrium, we're going to have 0.049
plus 2x and then x. So this should be equal to the silver squared, right? 0.049 plus 2x squared and then x for the chromate. Okay, if we don't want to solve a quadratic, we have to assume that the x is going to be really small, right? The x is going to be extremely small anyway for this compound in water, but it's going to be even smaller since we've already got a common ion there. So I think it's safe to say this is 0.049 squared then times x. So x is going to be 9 times 10 to the minus 12, right? Keeping x over here, but I flipped it. So this one divided by 0.049 squared. And that should be the molar solubility. I should have put an S in there to be consistent. We're talking solubility. S should be one of these. Okay. It means there we go. So we got 9 exponent 12, change the sign, and then 0.049 squared, and divided into that value is two significant figures, 3.7 times 10 to the minus 9 molar. Okay. One of the Itis brothers bothering me today. Let's see, can we get both of them on there? Yep. 36. How many moles of calcium fluoride will dissolve in 3 liters of 0.089 molar sodium fluoride solution? Okay, so this is going to be similar. We're interested in solubilizing calcium fluoride. Right, so we've got 1 calcium, right, and 2 fluoride ions. Right. The volume is 3 liters. Let's just put that out to the side. Volume equals 3 liters. And we're looking for the number of moles of calcium fluoride that will dissolve. Yeah. That's not the way you write that. That's the question. Okay, so initially, what do we have? 0.089 molar sodium fluoride. Right, so sodium fluoride dissociates in 1 sodium and 1 fluoride. So the molarity of sodium fluoride is the same as the molarity of the fluoride ion. So this should be initially 0.089 molar, right? And this one is 0. So what's the change? Well, obviously it's going this way. So the solubility is we're going to add some of this, right? One of these, or we're going to, that means that 2 of these are going to be added. We have S 0.089 plus 2S. Okay. So the KSP for this, for calcium fluoride is 4 times 10 to the minus 11. And that would be equal to S for calcium, and fluoride is 0.089 plus 2S, but that one is squared. Okay. We're gonna have to, unless we want to be here all day solving quadratic equations, we're gonna have to assume that that S is very small. All right, so we're gonna have S times 0.089 squared. There we go. Is equal to this. So S is going to be 4 times 10 to the minus 11 divided by the square root of that. This looks a whole lot like the one we just solved. Starting to get a little redundant here. 0.089, let's square that before we divide it. And that gives us two significant figures, 5 times 10 to the minus 9 molar. That's the concentration of calcium. But we got 3 liters, right? And in 3 liters, how many moles does that represent? Well, molarity times volume equals moles. So we need 3 liters times that. 1 point moles equals 1.5 times 10 to the minus 8 moles. Okay. Answer C. I guess that's the difference between this one and the previous one. We're carrying it one more step. Oops. Everybody still right? I'll start from the top there. All right, 37. What's the best way to ensure complete precipitation of SNS from a saturated H2S solution? We want to get this one precipitated from this one and this one. Oops, salt. There we go. This is a saturated solution of hydrogen sulfide. So we're saturated in this. And we want to ensure that we get everything, all of this tin out of solution. All right. If we add H2S, what's that going to do? Let's see. A. This is saturated. Right? So if we add H2S, what's that going to do? It's already saturated. If we add more of this, it's not going to make any difference. Right? So that one won't work. How about add a strong acid? What does adding a strong acid do? And strong acid. Well, if we add a strong acid, right, what does this do in solution? Right, it makes 2 of these plus 1 of these, right? Okay. If we add a strong acid, that adds this part of the equation and drives it back here. That's the one we want. It reduces that amount, right? So that makes this even less, and we're not going to get as much precipitation. We're coupling reactions here. So that one won't work. How about add a weak acid? A weak acid. Well, that does the same thing as the strong acid, only not quite as well. And so that one won't work. How about D? Add a strong base. Okay, say hydroxide. If we add a strong base, how does that affect? Does that give us more sulfide ions? Well, yeah. Combine this with that, you get water. It drives the reaction this way, makes more of that, you get more of that, which goes back here, and you get more precipitate. At a weak base, would not be the best option. It might affect it somewhat, but the strong base is the one that does the job. Questions? No? Okay. Seven. Okay. Let's see. When am I supposed to shut up? 11:15. Oh, we got another hour. That's good. My dad used to say, stand up to be seen, speak up to be heard, and shut up to be appreciated. Words of wisdom. Okay, concentration of magnesium 2+ ion in seawater is 0.052 molar. We just have to take their word for it. At what pH will 99% of the magnesium be precipitated as the hydroxide? Okay, so we're trying to precipitate magnesium hydroxide from magnesium 2+ in solution and hydroxides. Okay. We want 99% of 0.052 molar. 0.052 molar. We want 99% of that. So 0.99 would be the part of this that we want to drive the other way. Correct? I'm using a decimal equivalent of 99%. So 0.052 here, 0.99 times is, let's see, I'm going to keep a couple of 5.15 times 10 to the minus 2 molar. That's what we want to guarantee precipitating. Okay, excuse me. The KSP for magnesium hydroxide is 8 times 10 to the minus 12. And that's equal to, let's just be thorough. Oops. Nobody said anything. Okay. All right. In order to precipitate this, we need to know what's that value. If we know this value is 5.15 times 10 to the minus 2 molar, then we can solve this as an unknown. Find out what the hydroxide ion concentration needs to be. So OH, let's keep it squared, and we just say this one times that. Yeah, let's be thorough, since this is being recorded. Try not to skip any steps. Right? So I can say this, OH minus equals the square root of those two times each other, which would be 4.18 times 10 to the minus 13. You take the square root of that, which is 6.6, no, 6.41 rounded off to times 10 to the minus 7. Right? So that's the hydroxide concentration we need. POH, because we're going for pH, right? POH would be negative log of that value. Which would be 6.19. Let's see. I can only have two significant figures here.
two here, that means 2 decimal places. Okay, so I can keep 6.19, we're good. All right, so the pH then would be 14 minus 6.19. Which is, I did something wrong, let me try. There we go. 7.81.
Messed up.
Yeah, I did.
The 8.0 should not be 8.9 on some I guess well.
Yes.
Is 8.0.
Yeah, I 8.0.
There it is. That's the problem right there. Let's try it again. 9. Okay, so this is 4.58 times 10 to the minus 13. And let's take the square root of that. 6.77 to the minus 7. Then take the negative log of that. 6.17. Correct. 14. 7.83. That one up there. I still did something wrong. Okay, let's back up. Did I do this right? That looks right. I think it has something to do with that right there. Is this expression correct? Yeah. We know this value. What's this value? That one, this one, this one. But the hydroxide ion concentration is twice. Right, if we get one of these, we're gonna have 2 of those. Right, so shouldn't this one be 2x? I think that's where I made my mistake. That one should be 2x. So we have 4x squared. 4 that squared. So this one needs to be divided by 4 before we take the square root of it. Times and then divided by 4. So this one is 1.146. Now we'll take the square root of that. It is 3.3 times 10 to the minus 7. Then we'll take the log of that. Change the sign. 6.47. Still messed up, I think. 7.5. All right. Okay, I'm gonna have to cheat.
When you rearrange it to there's a way when you divide the 5.15 divided by 8.9 instead of multiplying it.
Yes. Yes. Okay. All right. I've wasted enough time already. Let me check myself out here. All right. It is just OH concentration. But this one needs to be divided. Four times the charm. 5.15 exposed. So divide. Okay, this one is 1.728 times 10 to the minus 10. Take the square root. 1.315 times 10 to the minus 5. And take the negative log of that. Is 4.88. There you go. And it's 9.12. Okay, 41. All right, let's see, I'm gonna have to scroll a little bit. There we go. A solution contains 0.018 moles each of iodine, bromine, chlorine, or chloride. When the solution is mixed with 200 milliliters of 0.24 molar silver nitrate, how much silver chloride precipitates out? All right. What we have to do to solve this one is put them in order. Which one precipitates first? It's going to take as much of the anion as it wants. And then when it's all gone, then the next one will precipitate if there's anything left of the silver. And then if there's anything left after that, the third one will go. Right, so what order will they precipitate? Well, we can compare the KSPs directly because we got one cation, one anion each. And so we know that the order is going to be as stated. Right, KSP is 1.5 times 10 to the minus 16 for the iodide. And then 5 times 10 to the minus 13. Yeah, and then 1.6 times 10 to the minus 10. All right. So this one's going to precipitate first. All right. It's going to, let's see. Actually, we can write it this way. Silver plus iodide, silver plus bromide, and silver plus chloride. And we've got 0.018 moles each of these. 0.018 moles of each one of these. Okay, how much silver did we add? Okay, silver concentration is equal to 0.24 molar, 0.24 molar times how many liters? 0.2. Right. So we're starting off with 0.048 moles of silver, correct? 1/10 of that would be 0.02, 2/10 would be 0.048. Okay. So that's what we're starting with. Okay. Let's see. 1 to 1, right? 0.018 moles. If we're starting off here, 0.048 minus 0.018 moles. So we have this much left over of silver after the first one precipitates. The second one's going to take out how much? Minus 0.018, which is 2, 1. All right, so that's what we have left after the second one precipitates. What's the question? How much silver chloride precipitates out in grams? All right, so this much silver is left over. We've got this much chloride, but 1 to 1 means that we're only going to get this much silver chloride. All right, we're going to have some, this is excess, and this is our limiting. So we're going to have 0.012 moles of silver chloride. All right, how many grams is that? Well, let's see. Silver, does it give us the, no, it doesn't, we have to calculate it. Molar mass of silver, 107.87, 107.87 for the silver, and then 35.45 for the chloride is 143.32 grams per mole. Okay. So 0.012 times that is 1.70 grams of silver chloride. Okay. Did I lose anybody? Okay. Right, 41. 43. Oh, 43. Okay, go look at our chart again. When a mixture containing cations of analytic group 1 through 3. So we're starting with groups 1 through 3. 4 and 5 don't matter. There's none of that in there. Treated with H2S in acidic solution. Acidic H2S. Which cations are expected to precipitate? 1, 2, 3, 1, 2, 1, 3, 2, and 3. Well, when you acidify it, group 1 comes out. Right? And then when you add H2S, group 2 comes out. That's it. 1 and 2. I think it's setting me up for it. Oh, this one looks bad, but it's really not. There's some that look bad and are, but not this one. Okay, the cation M2+ reacts with ammonia to form a series of complex ions as follows. So the first ammonia is added at a K of 10 squared. Okay, it's favored heavily to the right. The next ammonia is added at 10 to the third. It's even better. And then when you get the diamine of metal, you add another one. And it's favored way to the right. Okay. So what you have here is a situation where for each one, you've got a K. This one is like that, that was like that, that was like that.
So whatever ends up on the right-hand side is quickly taken up by this one. Favored, go to the right, go to the right, go to the right, go to the right. So overall, what you have is the formation of this complex ion. Three. And this charge. At the end, that's the dominant species right there. D. Right? If one of these were, say, I don't know, 10 to the minus 6, right, then that would essentially stop it, and the dominant would be the one above. But since they're all way to the right, way to the right, way to the right, the last one is the dominant. It makes it all the way to the finish line. And that's true for our diamine silver that we're doing today. It's favored way to the right for both reactions. Okay, 47. What's the concentration of nickel ion in 0.045 molar nickel nitrate solution that is also 1.0 molar ammonia, and the KF for that formation? Okay, so our equilibrium has all this nickel in that solution, and we're adding ammonia, and it's going to form the complex ion, and we're only concerned with formation constant and the equation that gives us that constant. So we've got nickel 2+ in aqueous solution, because all nitrates are soluble. Remember that one from first semester. And then ammonia in aqueous solution. All right, and how many of those do we need? 6. 6 of those? Yeah, 6 of those. And that gives us this complex ion. 6 of these with a 2+ charge. And this is still an aqueous solution. So all of these terms are present in the formation constant formula. Right? And then the reactants. Ammonia to the 6th power. And that's equal to 5.5 10 to the 8th. Okay, so what are we starting out at? 0.045 molar nickel nitrate. 0.05 molar nickel nitrate. And 1 molar ammonia. Go. And nothing there. Okay. So, let's see. What can I change? We're going that way. All right. So the concentration of nickel ion. Right. We want to know the final equilibrium concentration of the nickel ion. Want this one. So we're going to get something over here. For each one of these, we're going to get one of those. And we're going to lose one from this side. Okay. So how many of these do we have for each one of those? We're going to lose 6 of those. Okay, for every one of these. So 0.045 minus X, and this is 1, minus 6X, and this is X. So if we plug these values in, 5.5 times 10 to the 8th equals, let's see if I'm still on screen. Yep. This one is going to be what? This one's X in the numerator. This one, which is actually what we're aiming for, Once we find out what X is, then we'll have to subtract it from 0.045 to find out what the equilibrium concentration is. All right, so in this one, we've got 0.045 minus X, and we've got 1 minus 6X to the 6th power. All right, I don't want to solve. Let's see, what is it? Quadratic, cubic, quartic, quintic, sextic. I don't know. I don't want to have to solve one of those. So, no, I'm not sure what did I do in the. Can we assume? I make a mistake. Oh, I'm making it more difficult than it needs to be. Okay, hold on a second. Let's let this reaction go to completion before we go equilibrium. Let's do it 2 steps. Okay. So let's assume that all this nickel reacts with ammonia. So at the beginning, at our equilibrium beginning, nickel now is 0. And hold on a second. This was 0.045 molar. So this one would be, at our initial would be 0.045 molar. Did you see what I'm doing? I'm going 2 steps. I'm going stoichiometry first, and then I'm working backwards. Maybe we could solve it this way, but this is probably easier. Okay, so how much of this did it take? 0.045, 0.045, 6 times that much, right? So that's let's see, 3 and 24 is 27 and 2. I'll do that right. I better not trust my 0.045 and 6 times. 0.0270 here, okay. So this is what now that's what we used. This is what we used. 0.270 is 1 minus 0.270 is what's left over. 0.73. Okay, so when we go to our initial conditions, it's not 0.270, that's what we used. It's 0.73. 0.73. There we go. Okay, now we can go to our equilibrium. What kind of change? Now it's going to be shifting back this way. So we're going to have, and this is much better. Because now, if we solve for X, we got our answer. Okay, so if we got this much over here, that means we lost this much over here. Okay, and we gain 6 times that much over here. Okay, so we got X here, we got 0.730 plus 6X, and here we have, this is
6, 0.045 minus X. There we go. I think that'll work out much better. Okay, so let's change this. The expression is still the same. It just, we have different numbers. So, that one is 0.045 minus X. And since this value is so big, it's going to be mostly over here anyway. Right, before, if I did it the other way, I couldn't get rid of X because it was too big. But now, since we've gone all the way to this side and it's moving its way back, the X is very small. So the nickel is X, and this one is 0.730 plus 6x to the 6th power. Okay, and we can assume we're going to keep these two x's because they're not to any power. I think that's what I did. Did I do that? Now I got rid of that x2. Okay, so 0.045 over x times 0.73 to the 6th power. Then we solve for x. So I need to put x over here, put this one over here where x was, multiply it by 6 times that one, divided into 0.45. Okay, so let's see, 0.045, 5.5 exponent 8, divide that, and then 0.73 to the 6th power. Divide that into it. And this is 5.4 times 10 to the minus 10 molar. Yeah. Okay. Okay, is everybody okay with what I eventually did? Okay. Seven. I don't think I'm going to make it because these guys are kind of trouble. 50. Okay. The KF for the complex 1.7 times 10 to the 7. You know, when we actually do that lab today, most references give 1.7 times 10 to the 7 as the KF. That's the accepted value you're going to compare your work with. But I found at least one reference that was 1.1 times 10 to the 7. So I'm thinking if you get anything times 10 to the 7th, you're probably doing pretty good. The low end of 10 to the 7th. Okay, so KF for this one is equal to 1.7 times 10 to the 7. And KSP for silver chloride is 1.6 times 10 to the minus 10. Okay. Calculate the molar solubility of silver chloride in 1 molar ammonia. All right. We've got two equations here that are going on at the same time. One is silver ions plus 2 ammonias produce this complex ion. Here we go. With this KF. And this KSP is silver chloride solid produces silver ions plus chloride ions. And the question is, if we're looking for the solubility of this one, It's 1 to 1 here. It's 1 to 1 here. So the concentration, the solubility would be the same if we find out either the concentration of chloride or the concentration of silver in solution. And since this is 1 to 1, if we find the concentration of this one, it's also the solubility of silver chloride. All right, so I think we need to combine these equations. Since they're both going on at the same time, what would happen if we add these together? What K would be operating for that final expression? It would be this one times that one, correct? Multiply the K's when you add equations. So if we do that, then we've got the silvers cancel out. And we've got left over silver chloride plus 2 ammonias yield a complex ion plus chloride ions. That looks familiar. I think we're using that within our procedure. Okay, so the K for this one would be that one times that one. Let's see what the K is for this, for that expression. 7 and then 1.6 times 10. 2.72 times 10 to the minus 3. Okay, now how about the values that were given? The molar solubility of silver chloride in 1 molar ammonia. So initially, we have 1 molar here. And let's say we have none of that, none of that. Oh, this is better than I thought, because we still have this term. All right, so for every mole of this that goes into solution, we get one of those. For every mole of this, we get one of those. So what's the change? Well, we're going to lose some of this, right? But for every 2 of these, you get 1 of those. You know, I think, let's do away with fractions. Let's say, if we're going to get 1 of these on this side, that's X, that means we lose 2 of these. I think the math is better when we don't have fractions. Okay, so at equilibrium, we're going to have 1 minus 2x, and this is going to be x and x. Okay, so our expression here, this value is equal to x times x in the numerator, and then 1 minus 2x in the denominator, but it's to the 2nd power, like that. So if we solve for x, then we get the solubility. Maybe I should have called it S. Let's see. Oh, good. This is great. X times x is x squared, right? Okay. So that's equal to x divided by 1 minus 2x, whole thing squared. Okay? 2.72 times 10 to the minus 3. Okay, so if we take the square root of both sides, what do we get? Let's see, take square root of this one, and we get 5.22 times 10 to the minus 2. And the square root of this one is x over 1 minus 2x. Okay?
So if we multiply this one times that one, we get 5.22 times 10 to the minus 2 minus 2 times that x minus 1.04 times 10 to the minus 1 x equals x. Okay. So let's get x on one side. That means we need to add this value to both sides. Right. So if we add this one to that side, what does that give us? Well, that's 0.104, correct? 10 to the minus 1. No, it's, yeah, 10 to the minus 1. Yep. 10 to the minus 1. So on this side, we actually have 0. We have 1x plus 0.104x. Did I lose anybody here? I just added this to both sides since it's a negative. And that's 0.104. So 0.104 here and 1's already there. Okay. So that's 5, that's x, 5.22 times 10 to the minus 2. And now we just need to divide this one by 1.104. Yeah. This one's square. Let me do that again. 2.72. I'm gun shy now. No, I need to take square root of it. Square root of that, square root of this. 5.215. 5.22. And let's do, okay, we're good. Now I just need to divide this by 1.104. And x is equal to 4.72 times 10 to the minus 2. Should be the molar solubility. B. Okay. So the trick with this one is recognizing that this reaction is, these two are occurring in the solution at the same time. So we can combine them if we want. Yeah, it was 50. All right. $52. All right, this one is going to be complicated. All right, next, number 52. All right, 52. For the system, 500 milliliters of 0.02 molar manganese 2 nitrate mixed with 1 liter of 1 molar sodium oxalate. The oxalate ion actually forms a complex ion with the manganese with a coordination number of 2. So we've got the formation of the complex ion occurs in 2 steps. And the way it's presented here, the first step, the first oxalate ligand attaches to the manganese with an equilibrium constant of 7.9 times 10 to the 3rd. So it's way to the right. The second one, however, is written backwards. In other words, the complex ions on the left and the manganese the oxalate manganese complex ion is written on the right, it should be on the left, because if we go step by step, then the single ligand complex ion is reactant for the second ligand. So with that in mind, what I'm going to do is write the first equation as is and write the second equation flipped so that it's in the proper direction. I'll tell you what, no, I'll write them as is and then we'll do the flipping. Let's do it this way first. So the manganese 2 plus the oxalate ion, right? 2 minus is in equilibrium with, oops, not chromium, carbon. And that's 2 minus. You know what? Not 2 minus. Because the 2 plus and the 2 minus cancel. This is a neutral species. And the K for this one is 7.9 times 10 to the third. Okay. Now the second one is written completed complex ion where you have 2 oxalates. Since this one's a 2 minus and it came from a neutral, now the overall has 2 oxalates and it's a 2 minus charge. Now let's see, let's be consistent. There we go. And this is in equilibrium with MnC2O4 plus C2O4 minus, and the K for this one is 1.26 times 10 to the minus 2. All right. You know, we're going to flip this one because the correct equilibrium in stepwise is for this one to be inverted. Right? But we don't have to combine them, and it'll become obvious as we proceed. All right, so this one becomes the reactant for the second reaction. And it's equilibrium with the final complex ion. And the K for this one is just the inverse of that value, 1.26. 1.26 times 10 to the minus 2. Let's try that again. There. No. There we go. And then inverted. So now we get 7.94 10 to the minus 10 to the first power. There we go. Okay. What we're aiming at is to find out the concentration of this species right here. So we only need this equation, but in order to do that, we've got to find out what the other concentrations are. Okay, So let's do that next. What are we given? We're given 500 milliliters of 0.20 manganese nitrate. So what's the concentration before any reaction occurs? The concentration of each of the species. You know what? We do need to combine these reactions. Because this doesn't have manganese in it anywhere. That one has the manganese, and that's the information we're given. So we got to combine this one and this one to get an overall equation. So this one's going to be Mn2 plus, and it's in aqueous solution. Plus two of these, two oxalates. Now, why didn't I bring this one down? Because when we combine these two, they cancel. So that's the reactant side. The product side doesn't have any of this in it, but it does have the complex ion. Here we go. Now, if we were going to use this equation for the equilibrium step, we would combine this one and that one to give us this value. But we're only using this one to find out what's the stoichiometry. Right? What's the concentration of these before and after the reaction? So before the reaction, we have manganese is 0.02 molar and half a liter. So 0.02 molar and 0.5 liters, right? So half of this is 0.010 moles of manganese 2 plus. And what's the concentration before the reaction? It'll be 0.010 moles per the final volume. Final volume is a half a liter plus 1 liter is 1.5 liters. Well, let's see, before the reaction, the concentration of manganese is equal to 6.67 times 10 to the minus 3 molar. And the concentration of oxalate, because we put oxalate in there as sodium oxalate, sodium's just a spectator. The oxalate ion is the one we're after. So the concentration here is 1 liter, 1 molar, right? So 1.0 molar in 1 liter is equal to 1 mole of oxalate. What's the concentration? Let's see. Let's separate these two right here. There we go. So this one's going to be 1 mole per the same volume. So 1 divided by 1.5 is 6.67 times 10 to the minus 1 molar. Okay, and before the reaction, we have this and none of that. Right? We haven't gone that far yet. Okay, so after the initial reaction, if we take this reaction all the way to the right first, then we have 6.67 molar and 6.67 times 10 to the minus 1 It's 10 minus 3, 10 minus 1. The ratio is one of these for every two of those. But this is going to be completely used up. Right? So this is before, this is after. We're going to use all of this up. So now we have 0 molar of manganese. And after we have this one, actually, we're going to lose twice this one because it's 1 to 2. So 2 times this one is subtracted from that one, right? The ratio here is 1 to 2. So we're going to have this one minus 2 times 6.67 times 10 to the minus 3. Okay, so that's the after position, the stoichiometry of the oxalate. Right, 6, let's see, let me swap these and multiply by 2. Okay, this one is, well, this part is 1.33 times 10 to the minus 2, but we're going to subtract it from that value, which is 6.53 times 10 to the minus 1 molar. Okay, so this is the manganese concentration for our equilibrium step. Okay, and this is the oxalate concentration for our equilibrium step. And what does this one represent? Well, for every one of these, you get one of those. So all of this ends up over here as 6.67 times 10 to the minus 3 molar. So we got that for our equilibrium. We got this one, we got the oxalate at that concentration, and we have the manganese at that concentration. Okay, so now we're really only interested in this equation. Right? So if we take those values, and I'm going to erase everything down to here and keep those parts. Let's see, let's erase this one. Erase this one right here. 4. Here we go. And now, this one's the manganese. We don't need it because it's not in this equation. But this is the oxalate. So the oxalate concentration here is 6.53 times 10 to the minus 1 molar. This concentration, we don't know. That's our unknown. And this concentration is 6.67 times 10 to the minus 3 molar. And that's initial. So we can erase this now. This is our initial concentration for that equilibrium right there. Okay, so what kind of change are we going to see? Well, what we assumed was for the stoichiometry, we went all the way to this one. That means there's nothing here. Right? That means, actually, that's not X, that's 0. And change is going to give us some of this. So for every one of these, we get one of those plus X. And we lose only one of these over here. Right? How many of these do we gain? Well, for every one of these, we get one of those here. And the other one goes here. So it's only one here plus X, like that. I think I'm making this harder than it needs to be. Yeah, I think I'm making this harder than it needs to be. Yeah, because this one. Hold on a second. Let's keep going this way. Because I'm interested to see what happens. This one would be 6.53 times 10 to the minus 1 plus x. And this is 6.67 times 10 to the minus 3 minus x. Now, this value over here is very large. It wants to be way over here. So we're not going to lose much of that, and we're not going to gain much of this. So when we write the expression, 7.94 into the first, and that's equal to product 6.67 times 10 to the minus 3 minus x. And this is x. This is 6.53 times 10 to the minus 1 plus x. We know that these values are going to be extremely small because this wants to be way to the right. So this is approximately equal to 6.67 times 10 to the minus 3 divided by x times 6.53 times 10 to the minus 1. We just drop those two x's and solve for this x. Right? So this x comes over here. And that's the concentration of that species. That answers the question. Bring this one over here, put that one down here. So this one becomes 6.67 times 10 to the minus 3, 7.94 times 10 to the first power, times 6.53 times 10 to the minus 1. Yeah. Okay, so now we just need to crunch some numbers. Okay. 6.67 exponent minus 3 divided by 7.94 exponent 1 divided by 6.53 exponent minus 1. So I get, yeah. How many significant figures can we keep? We've only got 2. Yeah, we're limited to 2. So rounded off, this is 1.3 times 10 to the minus 4 molar. And that's equal to the concentration of manganese C2O4. Here. Okay. $53 is next. Go smoother. 53. Okay. What's the molar solubility of lead 2 chromate in 0.055 molar sodium thiosulfate? Okay. So the solubility of lead 2 chromate would be this equation. Yep, chromate. And then for this. And the KSP for that one is in minus 16. Okay. Okay. The thiosulfate serves as a ligand for the lead ion. So what we've got with the second one is we're taking this one. And we're combining it with the thiosulfate. And that would be, yeah, 2 minus charge. To make this product. I think I need 2 of them, don't I? Yeah, no, I need 3. 3 of these for the 4 minus charge. Need 3 here. Okay. Yeah. I'll keep going. And KF for this one is 2.2 times 10 to the 6. Okay. All right, so what if, let's see, is this balanced? One of those, one of those, one of those, one of these, 3 of those, yeah. We want to find the solubility of this one right here. So if we combine these 2 equations, then the lead ion cancels. And we're left with that one. I didn't cross out very well, did it? 3 thiosulfates. And then a chromate. And the complex ion. There we go. And the K for this one is that one times that one. (4.4 times 10 to the minus 10). All right, initial conditions, 0.055 molar thiosulfate. Okay. And 0 here, 0 there. Molar solubility. So the solubility, for every one of these, you get one of those. If this is the initial, then the change is going to produce something over here. And for each one of these, you get one of these. Correct? 0.055 minus S. Oh, excuse me. Minus S there, and 0.055 minus S here. And this is going to be S. So we should be able to solve for that molar solubility with this equation. 4.4 times 10 to the minus 10 equals, no coefficient there, no coefficient there. But we do have a coefficient here, okay. So that means in the numerator, we have S times S. And in the denominator, we have 0.055 minus S to the third power. Okay. This tells us that it's a very small value. It's going to move only slightly that direction. Right, so S is going to be very small. We can say that this is S squared divided by 0.055 cubed is equal to that value. All right, so I just need to cube this one and multiply it by that one, and then take the square root of both sides. So 0.055 and cube it is 1.66 times, this is 1.66 times 10 to the minus 4. Okay. And then I bring it over here and multiply it by that one, which is already in my calculator. And that's equal to, let's just say this. S is equal to the square root of this number, 7.32 times 10 to the minus 14. I'll take the square root of that. And S solubility should be 2.7 times 10 to the minus 7 molar. Okay. So the only one I did screw up one bad before. But the only one I have to go back and redo is 52. So I can do that after we finish our lab and splice it in. Let's see. Lab didn't start till what? 11:30? Okay. So take a break. And as soon as I need to check notebooks, don't I? Okay, I'll wait till everybody gets in here and then I'll check notebooks. Let's see. All right. I'm going to, let's see. I'm going to stop the share so I can pause it.